So today we conclude talking about method of undetermined coefficients by talking about some of the most complicated versions of these questions, which require us not only to solve the ODE, but to also find the solution which satisfies some initial value problem. For example, here we have an abstract problem that asks us to solve the initial value problem 2y double prime plus 3y prime minus 2y is equal to 14x squared minus 4x minus 11. So that's really similar to the things that we have done up to this point, but what's new is we also require some specific initial conditions to be satisfied. We want y of 0 to be equal to 0, and we want y prime of 0 to be equal to 0. So we're going to start by solving the ODE. So we're going to start by finding the complementary solution, what we called y sub c. Now, if I replace the function on the right-hand side with 0, I get a homogeneous ODE with constant coefficients. So I'm going to guess y equals e to the rx, and I'm going to get the auxiliary equation 2r squared plus 3r minus 0 minus 2 equals 0. Yep, that seems right to me. So this leaves me with two r values, 1/2 and -2, which in turn gives me two linearly independent solutions from which I can construct my complementary function. C1 e to the 1/2 x plus C2 e to the -2 times x. Next step is to find one particular solution using the method of undetermined coefficients. Now looking at my original ODE, the function on the right-hand side is a polynomial of degree 2. So I'm going to guess a polynomial of degree 2. ax squared plus bx plus c, which implies that yp prime is 2ax plus b and yp double prime is 2a. So let me go ahead and shove that data into our differential equation to determine the values of a, b, and c. So we had 2 times y double prime. We had plus 3 times y prime. And we had minus 2 times y. We wanted that to be equal to the expression on the right-hand side, which contained 14x squared minus 4x minus 11. So let's go ahead and algebraically simplify this, and as always I'm going to arrange these terms by who contains an x squared, who contains an x, and who is just constant. So we get the -2ax squared, and that needs to be equal to 14x squared. For x terms, we get a plus 6ax and a -2bx. That needs to be equal to -4x on the right side. And for constants, we get a 4a, we get a 3b, and we get a -2c, and that needs to be equal to the -11 on the right side. So I'm going to consider the constants only. This implies that from equation number 1, a must be equal to -7. And if I stick that into equation number 2, I get that 6 times -7 minus 2 times b is equal to -4. So -42 minus 2b is equal to -4. So -2b is equal to positive 38. and therefore b itself is equal to negative 19. So let's go ahead and shove that data into equation number 3. So now 4 times a becomes 4 times negative 7. 3 times b becomes 3 times negative 19. We have negative 2c. And that needs to be equal to the negative 11 on the far right. According to some calculator work that I've done on the side, this implies that negative 2c would be 74, and therefore c itself would be negative 37. So assembling those values, our particular solution would be negative 7x squared, negative 19x, and negative 37. In step number 3, assemble our general solution. Which has the form y equals c1 e to the 1/2 x plus c2 e to the negative 2x. That was our complementary function. And now we find that our particular solution has the form negative 7x squared minus 19x minus 37. Now, if we had just been asked to solve the ODE, we would be done as of step number 3. But we can't forget that we're in an initial value problem, and we also have to meet the 2 requirements that if we plug 0 into our solution, we require 0 to be the result, and if we plug 0 into the derivative, we still require 0 to be the result. So let's go ahead and calculate y prime, which would be 1/2 c1 e to the 1/2 x plus negative 2 c2 e to the negative 2x minus 14x minus 19. If I plug 0 into the original function, then I get c1 plus c2 minus 37. That has to be equal to 0. And if I plug 0 into the derivative y prime, I get 1/2 c1 minus 2c2 minus 19. That also needs to be equal to 0. So based on that, it looks, maybe I'll just do solving by substitution. It looks like c2 is equal to 37 take away c1. And if I shove that into the second equation, I find that 1/2 c1 minus 2 times the quantity 37 minus c1 minus 19 would have to be equal to 0. So we get 1/2 c1 minus 74 plus 2c1 minus 19 is equal to 0, which implies that 5/2 c1 is equal to 93. Which implies that c1 itself is equal to 186 over 5. So in order to now determine the value of c2, let's take this number and plug it into the equation c2 equals 37, take away c1. Which, in a somewhat unexpected turn of events, turns out to be just equal to negative 1/5. So now, having used the initial condition to pin down the complementary function's coefficients, we can finally get our final answer. The function y that we need is equal to c1, which was 186 over 5, times e to the 1/2 x, plus c2, which turned out to be negative 1/5 e to the minus 2x, plus the particular solution, negative 7x squared minus 19x minus 37. Let's acknowledge the fact that as we solved this problem, we didn't actually do anything new. Everything that we have done here is stuff that we have done before. We have already plenty of times now solved a homogeneous constant coefficient ODE. We have already plenty of times now used method of undetermined coefficients to locate a particular solution. And we have already solved initial value problems by plugging the initial condition into the functions and using those to determine the value of the constants in the complementary part of our solution. What's new is just having to do all of this all together in one problem. Let's do one more example in an applied problem. As we have mentioned, a circuit that contains all three varieties of component, an inductor, a resistor, and a capacitor, can be represented using a second-order differential equation with constant coefficients. If I take the inductance and multiply it by the second derivative of the charge, the resistance and multiply it by the first derivative of the charge, and 1 over the capacitance multiplied by the charge itself, then that is equivalent to the impressed voltage on the circuit. So with that differential equation, let's consider the following exercise. They say, okay, as a hint, the relationship between the quantity called Q and the quantity called I, which represents the current, is that the current is equal to rate of change of charge over time. I is equal to Q prime. So with that note, let's go ahead and let's try and answer the following question. Let's find the charge, let's find Q. If we have an inductance of 1/2, so 1/2 Q double prime, a resistance of 10, so 10 Q prime, a capacitance of 0.01 times Q, and a voltage of 150, constant. But we also have some initial conditions here. We're given that the charge is initially 0, and the current is also initially 0. But using the hint, we can rewrite the second initial condition as Q prime of 0 equals 0. So let's go ahead and solve this initial value problem. The first thing that I'm just going to do is I'm going to clean this up a little bit. Instead of 1 divided by 0.01, I'm just going to rewrite this as 100. And for convenience sake, I'm also going to multiply everything through by 2 so that I don't have any fractions. So as always, step number 1 is to find the complementary solution. So in this case, it might be called Q sub C, the complementary function in the case that our output variable is Q. So we are solving Q double prime plus 20Q prime plus 200Q equals 0. And since we have constant coefficients, we're going to guess that the solution has an exponential format. I guess this should really be time. So I'll do RT. So we get the auxiliary equation, r squared plus 20r plus 200 is equal to 0. Negative b plus minus the square root of b squared minus 4ac all over 2a. So if I simplify that, we get two complex roots, negative 10 plus minus 10 times the complex number I. So that gives us the two real valued solutions, e to the negative 10x, t for time is more appropriate, and q instead of y, goodness me. Negative 10t cosine of 10 times t. That's our first linearly independent solution. And C2, e to the negative 10t sine of 10t. So now I'm going to guess a particular solution. I'm going to guess a YP, and I'm going to have a look at the right-hand side of my original differential equation. So in this case, the function that we have on the right-hand side is 300, which is a constant. It's a polynomial of degree 0. So I'm going to guess that my particular solution is also constant. And if I plug that into my differential equation, I get 200 times a, because q prime and q double prime are gone. Oh, this should be q, q, q. $200 times a needs to be equal to 300. And so my particular solution is just 3 over 2. So step 3, we achieve the general solution to our differential equation, which has the form q, haha, I got it right this time, q equals c1 e to the negative 10t cosine of 10 times t plus c2 e to the negative 10t sine of 10 times t plus the particular solution, which is equal to 3 over 2. Now, let's use the initial condition to determine the values of C1 and C2. We require that the charge is initially 0, and we require that the current, the derivative of charge, is also initially 0. So in order to be able to plug 0 into the derivative of charge, we're going to need to find the derivative of the function q of t written above. I'm going to need more space for that, I think. So if I calculate the derivative of the first term, I'm going to need to use product rule. So the first times the derivative of the second plus the second times the derivative of the first that's the derivative of the first product in q of t. For the second product, it'll be similar but with sine instead of cosine. So we have the first times the derivative of the second plus the second times the derivative of the first. The derivative of the final term, 3 over 2, that's a constant, so its derivative is equal to 0. Now, if I plug 0 into this derivative, the terms containing sine are going to vanish, and all that will be left are the two terms containing cosine. So q prime of 0 will be negative 10 c1 from the first term here in the back, positive 10 c2 from this expression. If I plug q0 into the original function, the sine term is going to vanish, and I'm left with c1 plus 3 over 2. So that's pretty convenient. From the first initial condition, I can tell right away that c1 is going to be negative 3 over 2. From the second condition, I can tell that c1 and c2 are going to be equal. And therefore, if I combine these facts, that means that c2 also has to be negative 3 over 2. So what is the charge at any given time? The charge is given by negative 3 over 2 e to the negative 10t cosine of 10 times t minus 3 over 2 e to the negative 10t sine of 10t plus the particular solution of 3 over 2, which we calculated. This function will give us the charge on the capacitor at any given time. Now someone says, follow-up question, based on what you calculated, what's going to happen to the charge in the long run. In other words, what happens to Q of t as t, representing time, gets really, really large? Now, when time gets really, really large, the e to the negative 10t will go to 0, because we're raising e to increasingly negative powers. So both of the two terms containing e to the minus 10t will vanish over time, and the charge on the capacitor will level out to a value of 3/2, the constant left in the back. That concludes today's material. Nothing new, really. We just practiced using the techniques that we have already developed to solve some initial value problems containing non-homogeneous ODEs.